All right. Hello there. Let's bring it in. Bam! All right, so this is my first attempt at using Zoom for virtual office hours, and I don't know that anybody's going to show up. So I'm going to try and experiment using this to recap chapter 22. So let's see how this works. Share screen. Let's go to chapter 22. Okay. So I'm going to do a little recap of chapter 22. And these are my lecture notes, and I am going to email these out to everybody, hopefully tonight. So just as a little review, we started off with a brief review of atoms. And so let me actually do a new share, see if I can start. Hey, it works. Okay, so just as a brief little recap, remember the atomic structure is basically, this is our model of the atom. And again, this is not a realistic model. Atoms are mostly empty space, 99.99999999999% empty space. So our typical model is we've got a nucleus, which consists of protons, which are positively charged, neutrons, which have no charge, and surrounding the nucleus, we have electrons, which have a negative charge. Keep in mind that we do not really know what electric charge is. It's the name we've given to this property that attractive and repulsive behavior of protons and electrons is attributed. So we don't really know what charge is, but we've given it the name to this property that two electrons will repel each other, two protons will repel each other, a proton and an electron will attract each other. Just a few important facts about atoms. We know every atom has a positively charged nucleus surrounded by negatively charged electrons. All electrons are basically identical, meaning they have the same mass, same charge. Same thing with protons, they're all identical. Every proton has the same mass, same charge. Protons, positive charge, electrons, negative charge, and protons have about 1,800 times more mass than the electron. So most of the mass of an atom comes from the nucleus, the protons and neutrons. The size of an atom has to do with the electrons. And important point, most atoms are neutral because they have the same number of protons as electrons. And then our big starting point for the chapter is like charges repel each other. So two negative charges will repel each other, two positive charges will repel, and then opposite charges attract. All right, so going back, let's go back to lecture notes. So opposite charges attract, like charges repel. And I mentioned that electrical force is unbelievably strong. The proton and electron, since they have mass, they're going to attract each other gravitationally. Since they have opposite charges, they're going to attract each other electrically. And the electric force is about 1,000 trillion times stronger than the gravitational force. So the question is, if electrical forces are so strong, why do we not usually feel them? And that's because most objects are electrically neutral. Whoops. They are electrically neutral because they have the same number of protons and electrons. I don't know why it's not letting me do this now. Okay, let me switch. Actually, let's stop this share for a second. See if I have any participants. Manage participants. Hey, it's just me. Okay, that's fine. So let's go back to sharing. Let's share screen. Go back to my notes. Okay, so most objects are electrically neutral. Oh, maybe it's not letting me draw. Let's see. Annotate. There we go. Draw. So most objects are electrically neutral because they have the same number of protons as electrons. Let's use red. So how does an object become charged? Always by gaining or losing electrons, never protons. Why not? Protons are trapped in the nucleus by the strong nuclear force. Basically, protons cannot escape the nucleus. So anytime something gets charged, it's by gaining or losing electrons. If, let's see if I can scroll up or down, it's not letting me do that. If an atom loses an electron, actually let's do it. If an atom gains an electron, it becomes negatively charged. We call that a negative ion. And let me stop there. Where can I do? I want to select. Nope, I want to mouse. Move this up. Ooh, I guess I need to erase this annotation then. Still learning this. Okay, so getting to the mouse again. Eraser. Okay, so I also mentioned in class that it's always the outer electrons that get transferred. Let me draw. Why is it the outer electrons that are transferred? Because basically they are very loosely bound. The farther away an electron is from the nucleus, the more weakly bound it's going to be. So anytime charges are getting transferred, it's always electrons being transferred from one object to another. Okay, in terms of conductors and insulators. So what is a conductor? A conductor is just something through which electric charge can easily transfer. So something that transfers electrons very easily. Basically, good conductors are most metals. So gold, copper, aluminum, things like that. What makes something a good conductor is there's some electrons that are not anchored to any particular atom and are free to move around. An insulator is something that charge cannot flow easily through. And what makes something a good insulator is all of the electrons are tightly bound to the atoms. So things that are pretty good insulators, we've got glass, rubber, plastic, wool, pure water. So water in general, tap water, is a pretty good conductor. But if you had just pure filtered H2O, that in itself is a pretty good insulator. So let's erase this again. Continuing forth, Coulomb's law. So Coulomb's law is basically the law that relates the force between two charges. The equation is the force between two charges is K Q1 Q2 over D squared, where Q1 and Q2 is the charge on each object in coulombs. D is the distance between the charges. The important thing to note here is that the force goes like 1 over r squared. So two important things. The bigger the distance, the weaker the force. The smaller the distance, the bigger the force, but it depends on r squared, which means if I had two charges exerting a certain force on each other, and then I move those charges so they were twice as far apart. So now it's 2 times as far apart. Because it's 1 over r squared, the force is weaker when the distance is bigger, but it's not twice as weak. It's actually 2 squared, 4 times weaker. Okay, and then moving on, we looked at different ways of charging an object. And in fact, let me go to PowerPoint to talk about that. Okay, so the 3 different ways of charging an object. One, we've got, let me draw this, charging by friction. And anytime you get a static shock, it's basically charging by friction. You have 2 materials that rub together, you can get electrons being transferred from one material to another, charging by friction. Charging by contact is if you have an object which is already charged. So let's say you walk across the carpet and you get charged. If you go and then touch somebody else, you can charge them by touching a charged object to an uncharged object. We call that charging by contact. And then charging by induction is a little bit more challenging. One, you're not rubbing 2 materials together, so it's not charging by friction. 2, you're not touching a charged object to a neutral object, so it's not charging by contact. So let's mouse. Why can I not? There we go. Up, let's erase this stuff. Mouse. Okay, so a couple things. One, why does a charged object get attracted to a neutral object? And the answer is, let's say I charge a balloon negatively. How can I stick it to the wall? The balloon will do what's called polarizing the wall. So the wall is still neutral, but if you notice, one side of the wall is positively charged, the side closest to the negative balloon. The other side of the wall is negatively charged. So the negative charges will repel the negative charge in the wall, attract the positive charge. So the balloon is going to be attracted to the positive side of the wall. Whoops, that was horrible. Let's try a stamp spotlight. That's not gonna work. Draw again. So the balloon is attracted to the positive side of the wall. It's going to be repelled away from the negative side. But since the positive charges are closer, force depends very strongly on distance. The closer the charges, the stronger the force. So the fact that the balloon is closer to the opposite charges of the wall means that attractive force is going to be stronger than the repulsive force. Okay, so let's just talk quickly about charging by induction. So let's say I had a metal sphere, metal meaning it's a conductor, so the electrons are free to move, and I bring a negatively charged rod nearby. Here, this is charging by contact because I have a charged rod touching a neutral object. But let's say I have a metal sphere here, and this is a conducting sphere. It has a bunch of positive and negative charges, but the negative charge is free to move around. I bring a negatively charged rod nearby, and what that's going to do is it's going to repel all the electrons to one side, leaving one side of the sphere positive, the other side negative. It's still neutral because no charges have been transferred onto or off of the sphere. So now it separates the charge. Ideally, this negative charge would want to get as far away from the negative rod as possible, but it's trapped on the sphere. But if I supply a grounding wire so that now electrons can travel off the sphere, what's going to happen is they're going to get repelled away from this negatively charged rod, leave the sphere. The end result is the sphere has lost a bunch of electrons, so it's negatively charged. I'm sorry, it's lost a bunch of electrons, so it's positively charged. So I've charged it positively with the help of a negatively charged rod. Okay, let's stop that share. Oh, a couple other things, actually. Let's start that share again. Share screen, blah, 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 blah. A couple things. Lightning, don't worry about for the celebration. Induced charge again. Like, how can I rub my hair with a comb and then use the comb to pick up pieces of paper? What ends up happening is in this case, oops. I want to annotate, draw. So I've got a negatively charged here rod, and let's say this is a piece of paper. Again, even though paper is an insulator, you can actually have individual atoms becoming polarized. So like this represents an atom that overall is neutral, but I have more electrons on one side of the atom than I do the other. Again, this rod, or let's say this piece of paper, is going to be attracted to the negative rod, the positive side. It's also going to be repelled away because opposite charges attract, like charges repel. But the fact that these positive charges are closer to the rod than the negative charges means overall there's going to be a net attractive force. Okay, mouse. Eraser. Okay, electric fields, don't really worry too much about electric fields for this chapter. Basically, what we now understand is that if I have a charged sphere or something like that, the reason two charges will attract each other. We used to think I'd say, okay, this positive charge is attracted to this negative charge. But what we now know is if I have a charge here, it completely changes the space around it, creates what's called an electric field. And what ends up happening is that the electric field from one charge that actually exerts a force on the second charge. Huh. So that's sort of a quick little recap. And let's stop this share. Still just me. Hi, me. And then let's do a little review of the homework. So yeah, what I want to do is during office hours, sometimes I will go through the homework, or maybe I'll do that as just a separate lecture. So let's go through this homework for chapter 22. And let's make sure I can annotate, draw. Okay, so question number 1. Why are objects with vast numbers of electrons not normally electrically charged? The number of electrons in our body is insane. I couldn't even give you a number, 10 to the 30, maybe something like that. Why does that mean we don't have a huge charge? Because for every electron in our body, generally there's a proton. Objects are usually neutral because they have the exact same number of positive charges as they do negative charges. They have the same number of protons as electrons. Okay, 2. Why do clothes often cling together after tumbling in a clothes dryer? The reason is this has to do with charging by friction. So you have 2 materials that are rubbing together inside the dryer as they're tumbling around. Because of those 2 materials rubbing together, or clothes rubbing against the side of the dryer, you can get charging by friction happen. And so the 2 materials rubbing together, electrons can be transferred from one to the other, making one object positive, the other object negative. And that's the reason that clothes cling together, is because charging by friction happens, the clothes become charged, and you can have a charged object being attracted to a neutral object. 3. Strictly speaking, when an object acquires a positive charge by the transfer of electrons, what happens to its mass? What happens to its mass when it acquires a negative charge? Think small. So electrons, although they're really, 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 really small, they do have a teeny tiny mass, which means if you lose an electron, you lose the mass associated with that electron. If you gain an electron, you gain the mass associated with that electron. So an object that's negatively charged means it's gained electrons, which means it's going to have more mass than when it's neutral. An object that's positively charged has lost electrons, which means it's going to have less mass than when it's neutral. Okay, mouse. Let's move this up. Let's erase these. Okay, 4. How can you charge an object negatively with only the help of a positively charged object? Let's see if I can just do this. Erase. So I'm going to do this down here. So this is charging by induction. So we want to know, how can you charge an object negatively with only the help of a positively charged object? So let's say I have a positively charged rod. So I have a bunch of excess protons. Basically, this rod has lost a bunch of electrons. And I bring it near a negatively charged, or I'm sorry, a neutral conducting sphere, which means it has a bunch of positive and negative charges in it. Well, what that's going to do is cause a bunch of electrons to move to one side, a bunch of protons, positive ions, to move to the other side. Overall, the sphere is still neutral. But now, if I were to connect a conducting wire to it, what's going to happen is this conducting wire is going to allow a bunch of electrons, because they're going to be attracted to this positive rod. Some electrons are going to transfer onto the sphere. The end result is the sphere has gained some electrons, leaving it negatively charged. Okay. Let's go back, erase this. Okay, mouse. Okay, so going back, let's take a look at question 5. When one material is rubbed against another, electrons jump readily from one to the other, but protons do not. Why is this? Again, protons are trapped inside the nucleus by the strong nuclear force, in essence, they can't escape the nucleus. So it's always, always, always electrons that are getting transferred. 6. How does the magnitude of electric force compare between a pair of charged particles when they are brought to half their original distance of separation, 1/4 the original distance, 4 times their original distance? So again, the key here is that force goes like 1/r². So the things to keep in mind: bigger the distance, weaker the force. But whatever happens to the distance, you square that, and that's what happens to the force. So if something is brought to 1/2 their original distance, that means they've gotten 2 times closer. The force is going to be stronger, but not twice as strong. It's going to be 4 times stronger. So in half the original distance, it's going to be 4 times stronger. To 1/4 the original distance means it's 4 times closer. 4 times closer means a stronger force, but not by a factor of 4, by a factor of 4 squared, which means it's going to be 16 times greater. And then how about to 4 times the original distance? Again, if we change the distance by a factor of 4, the force changes by a factor of 16. Here, if I bring them to 4 times the original distance, it's 4 times farther apart, which means the force is weaker. But in this case, it's 16 times weaker. So the force would be 1/16 the original force. Okay, 7. Oh, I can just clear everything. 7, when you double the charges on both particles in a pair, what effect does this have on the force between them? Does your answer depend upon the sign of the charges? So Coulomb's law says the force is proportional to the charge on each object divided by the distance squared. And there's a constant in there. But if I were to just double one charge, the force would double. If I double both charges, the force doubles twice. The force changes by a factor of 4. So if I double both charges, meaning now they have twice as much charge as they did before, the force between them will increase by a factor of 4. Does the answer depend upon the sign of the charges? The answer is no. If they're opposite charges, they're going to attract. If they're like charges, they're going to repel. But it doesn't matter if you double both charges, the force is going to change by a factor of 4. All right, is it clear? Clear all drawings. Oh, sweet. Mouse. Let's move this down. 2 more. Okay, draw again. 8. If you rub an inflated balloon against your hair and place it against a door, by what mechanism does it stick? Explain. So again, let's say here's a wall. It's got a bunch of positive and negative charges, and here's a balloon. And the balloon, let's say, is negatively charged. What that's going to do is repel negative charge in the balloon or in the wall, moving it farther away, and attract positive charge. So the end result is the wall is still neutral because no charges have entered or left the wall. But the balloon is attracted to the positive side of the wall. It's repelled from the negative side. But again, force is strongly dependent upon distance. So the fact that the opposite charges, the positive in the wall and the negative in the balloon, are closer together than the like charges, the negative in the wall and the negative in the balloon, means the attractive force is slightly stronger than the repulsive force. And last but not least, number 9, your friend. A friend says that the reason one's hair stands out while touching a charged Van de Graaff generator is simply that the hair strands become charged and are light enough so that the repulsion between strands is visible. Do you agree or disagree? In this case, the answer is you agree. Like charges repel, and when you touch a Van de Graaff generator, the charges transfer from the generator to you, into your hair, well, into all parts of you, but your hair is light enough that the repulsion can cause them to stand up. Whew. All right, so let's stop that share. So we'll see how this works. I'm going to upload this to YouTube and then send out a link tonight. But this will serve sort of as the lecture for Tuesday. I will do some more tomorrow and upload another video, probably just introducing chapter 23 on electric circuits. please, please, please take the time to read it. And what I think I'll do is I think I'm going to upload a PDF of the book. I know that some people don't have it and I'm going to the library, and so I want everyone to have access to it. So anyway, I will be sending out an email tonight. Stay tuned.